algebraic reduction. Thank you. Go ahead.
Okay, yeah. Switch that on. Can you hear me? Yeah? Okay, good. Yeah, thanks a lot for the invitation. It's a pleasure to speak here at IGST in London after 10 years once again. So today I'll talk a bit about classical and quantum algebra related to Magnons, some old stuff. And this is work to some extent already done with Diego Im, and also work in progress also together with Hannes Malcher. So just as a overall scope, so we do have an exact S matrix for Magnon scattering on the worldsheet, and the way it was first found was through symmetries. So in fact, this S matrix can be fully constructed through or as usual in integrable systems, you can construct an S matrix fully through the extended quantum symmetries or classical quantum symmetries. And of course, we know that this S matrix or R matrix has found multiple applications in ADS-CFT integrable systems, but it's also a somewhat particular S or R matrix for quantum integrability, for quantum algebra, in the sense that it, for example, doesn't have a difference form, and thus there are also a couple of open questions, in particular regarding the symmetry. So for example, what is the complete symmetry algebra that is related to this R matrix? Are there any extra symmetries? How about boosts that allow you to go from one reference frame to another? Or maybe there are some central charges. Also, what could be the relation to standard quantum algebras? I mean simple quantum algebras, for which quite a lot is known. And finally, can we construct a universal R matrix for that resulting algebra then? And then if you want to obtain a universal R matrix, it's probably useful to know the full complete symmetry algebra. So for the purposes of this talk, my goal will be the formulation of a complete symmetry algebra for this Magnon scattering picture. And I'll just start with a bit of motivation. Or the status quo. Then I will present how you can obtain this algebra from a more standard Poincare type affine symmetry or super algebra. And at the end of the talk, I should comment a bit more on the quantum aspect, but start first with the classical one. So here, as a reminder, of what we know about Magnon scattering, or for this R matrix, it basically all started with, say, a dynamic spin chain obtained from n equals 4 super Young mills, and I will mostly refer to the most symmetric system, which is n equals 4 super Young mills, but to some extent, of course, also this R matrix has applications in slightly lower symmetries and lower symmetric systems. Anyway. So here, the usual QQ relation has an energy coming out, and the unusual feature for this dynamic spin chain was that you can also find non-trivial Lie brackets or supersymmetric Lie brackets for these supercharges of the same type. And that led us to this PSU 2/2 super algebra for the Magnon picture with an additional three-dimensional center. And this three-dimensional center is not just anything, but it had has some curious expressions which relates all these three central charges in a certain way. This is something more like an energy, whereas these two serve more like a momentum purpose for these magnons that travel on the spin chain or on the worldsheet. And some improved understanding came about by looking at the classical limit. Classical limit where we take h bar to be small. H bar is 1 over g or 1 over square root of the 't Hooft coupling. And at the same time, also these momenta should probably be small. And by investigating this classical limit, we found that the symmetry algebra is actually something much like a U2/2 algebra, which is PSU2/2, but with one additional central charge and one additional derivation. And well, that's somehow different from that picture. We only have one generator P, and we also found an extra symmetry through looking at those classical algebras. It's also a loop algebra, so we do have a spectral parameter that means that all of these generators get lifted to arbitrary loop level in this loop algebra sense. So that is what you usually have in integrable systems. But also, this symmetry admits an affine extension where you have one additional U1 and one additional central charge, something like a derivation that basically measures the level here. And the central charge is something that is sometimes used in affine representation theory of affine Kac-Moody algebra. Heavily depends also on this central charge. But so far hasn't really found an application in the integrable systems because it was always just 0 for the type of representation we looked at. But that leaves quite a few open questions related to the algebraic treatment. For instance, first, why do we have this three-dimensional momentum vector in the first place? Why do we have these curious functions? Why do they have that particular form here? How does this three-dimensional momentum reduce to merely one generator? And if it does reduce to one generator, why don't we, I mean, we should see a two-dimensional picture from the world sheet, which has energy and momentum. So how do these numbers mix up? What is the nature of this extra symmetry L that came about in the classical discussion? And what about their loop levels? Can we make sense of the affine derivation? Is there some purpose of changing the reference frame somehow from one to the other? Or could this derivation even be extended to a Möbius or a Witt or Virasoro algebra? Would that make sense? And then would the central charge of the affine algebra perhaps play a role? And eventually, how can we quantize the full classical affine algebra? So at first, I'll start with the classical algebra here. And yeah, just start with this aspect that we have three central charges and try to make sense of that. Namely, this three-dimensional momentum might well belong to a three-dimensional or 2 plus 1 dimensional Poincare algebra, which is SL2 cross C3. And it might be useful to relate this to a simple algebra, and the useful relation is to the algebra of SO4 or SO2,2, which is two copies of SL2, because you can obtain a Poincare algebra from a curved rotational algebra by a contraction. Contraction means that you just change the generators in a certain way, and then you take a certain limit on this transformation that makes this singular. And in this way, you can obtain from this simple or semi-simple algebra, SL2 cross SL2, you can obtain this non-simple algebra, which is the Poincare algebra. And in fact, this picture has a supersymmetry extension where you basically just squeeze this PSU2/2 algebra in between the two factors. And one can even obtain this as a contraction, as we found out a couple of years ago. And that sort of makes it, very exciting for our purposes. So in particular, we do get this exceptional super algebra D21 epsilon, I called it, because epsilon is supposedly small in this limit. You pair that with an SL2 and you can get a Poincare extension, supersymmetry extension. Now, why is that useful? Well, we might, if we follow this picture through, we might obtain the integrability structures from a simple classical or quantum algebra or superalgebra, namely this one. And for simple algebras, the construction principles are quite well established, so we could eventually even obtain the universal R matrix from this. It's also curious, the participating R matrices that you get from here. There are two, actually, one R matrix from here and one of there. And once you do the contraction, you sort of marry them up and you cannot take them apart afterwards. So that adds some interest into this picture. And what's also curious is that if you take a loop algebra or an affine algebra of a semi-simple algebra that is a product of two simple algebras, you actually have two independent spectral parameters to start with, and then these even survive in the contraction process. So if you take this honestly, then actually there is an additional spectral parameter which might somehow play a role. And there's also a center which could have some meaning. Okay, so back to our problem. We do have three momenta. We also have three rotations in this Poincare algebra, and we just want one momentum, but we maybe also want one rotation generator L. And how do we do with that? Well, in 3D, you can just pick a direction. You restrict to rotations around this one direction, and you also restrict to translations along this direction, and that forms a proper subalgebra of Poincare. In fact, the reduction is a bit different here. For the rotations, you take a subalgebra. For the translations, you rather take a projection. You only want translations in a certain direction. But yeah, that would be a way to reduce this 3 plus 3 dimensional algebra to a 1 plus 1 dimensional algebra that we want. But it's just too plain for ADS-CFT, because once you pick a direction, that might just be a time-night direction, so you just pick a static reference frame and rotations, so that makes it a bit boring, and the ADS-CFT R matrix is not of this form. But instead, you can choose this reference vector here to depend on the spectral parameter in a certain way. If you choose this, say, then this direction of rotation would take this form, and the momentum vector would also take a particular form. And they depend on the spectral parameter in the sense that U times L to the 0 would just mean the first loop level of the L0 generator, and that really adds some new features into this algebra. But still, this procedure works. You can reduce the algebra in this way, and even the co-algebra reduces nicely. But you cannot do this for any arbitrary vector. It has to be basically of a very simple form like this one. And it only works if you do a twist of the Poincare R matrix in the first place. And the twist is of this form, where you take one Cartan generator and a raising generator. And I'll talk a bit more about that later. There's also the affine derivation that you can get from this Poincare algebra, or loop affine Poincare algebra. But in order for this to make sense, you have to adjust the derivation in a bit, because the derivation is just shifting the spectral parameter U here. But if we do shift the spectral parameter U, of course, the form of this L would also change, and it would run out of the algebra. And in order to make it a closed subalgebra, you have to make sure that this one closes with the derivation. And this is done by adding in some extra rotations. However, these have to depend on U, and that leads you to some funny conclusions. Might not be so apparent to you, but one thing that's very curious is that now you get additional singularities at a certain value of the spectral parameter U, which is plus or minus 2. This is actually where particles, magnons, become very fast, light-like, and once they become light-like, of course, you might expect something strange to happen. But the algebra relations become odd because you have additional poles in here, and that adds some complications if you want to work with it. Okay, let's just try to make sense of what I said so far and wrap up a bit. So if we have a Poincare algebra, well, the irreps are usually labeled by a mass and a spin, even in 3D. But the states of a loop or affine algebra are also labeled by the spectral parameter U. So the momentum is going to be a function of U, and the energy is also a function of U, and there's a certain relation that was obtained through this reduction. But nicely, it's not just a static picture, because we do have representations with different energy and momentum. We do have extra symmetries. These L's are rotations around the particle axis of motion, if you wish. So that's just a spin generator. And we have ADS-CFT, we have bosons and fermions, they have different spin. So this L will basically rotate the bosons against the fermions, and that's how this works. You can also do this at different U of n, so basically this adds, for your phase degree of freedom, this adds a momentum dependence. So basically you can gauge transform your bosons against the fermions. So it sounds a bit like a gauge symmetry, what you have there. The derivation basically shifts U, but since U is coupled to the momentum and energy, it somehow shifts the reference frame. So this D derivation is something like a Lorentz boost, but it's not really a Lorentz boost. You could introduce this special relativity, rapidity variable, and a Lorentz boost would just be a shift of rapidity. But here there's an additional factor of p squared. What's interesting though is that you do have here a non-trivial co-bracket for D, and that sort of is what's at the heart of the non-difference form of the S matrix or R matrix, because D is like a shift of U. If you shift both U's by the same amount and nothing changes, then it's of a difference form. But here you change the U's, and the co-bracket will be non-trivial, and that just means the S matrix changes under such a transformation. So that is non-difference form. But there, you can see this Lorentz boost, but you just have to multiply this D by 1 over p squared to make it a Lorentz boost. So it sort of feels a bit related, but it's not exactly the same. Okay. So that's basically all you can and we got from the classical picture. And now let's take a step back and maybe do something else. So you might know me as someone who sometimes steps out of the ordinary and tells you about things that you don't want to hear about or don't really want to hear about. So I have to be true to myself and do that. And here comes my little commercial break. Namely concerning something about LaTeX. So maybe you want to compose well-balanced LaTeX documents or prepare appealing slides, maybe not like mine, but maybe you want to do this directly in LaTeX. And of course, as you know, many things work nicely in LaTeX. So, or you take some packages like Beamer, be happy with that, and most of the time that works out nicely. But sometimes you want to do some adjustments or fine-tuning that doesn't really work so well, is really a hassle to code. And some examples of that might be you want to position included graphics, or you want to compose limiters and change them to your needs, or you want to compose some multi-line equations and they don't come out right the way you want. So maybe you want to handle these aspects more at ease. Maybe you're a person who enjoys both a perfect output and clean sources. If not, then, well, okay, you have to bear with me for a couple of minutes, but I'm certainly such a person, and that's why I got annoyed by things and changed some things. And so out came some packages that you may or may not use. One of them is Graphbox, which allows you to quite easily shift graphics around, or just punch them on your document without occupying space. There is something to code graphics, not using ticks as many people do, but MetaPost is sort of similar, and that's what I use to draw most of my figures. I've also composed some fixes for math mode that I like. But maybe most importantly, I've spent some time this year to write up something on multi-line equations, which allows you to do some options with them. And so I wanted to just use this opportunity or non-opportunity to highlight two packages, namely delimset and this equation lines. And the purpose, motivation is that if you don't know about it, then how could you use it? So I'll let you know about it. And okay, here. here comes the first package, and just a brief, instance of unwanted user support. So this is a package that declares this delimiter structures, which are brackets. Now, if you want to code something like a plus b in brackets, you could just use this command to put the brackets. And you would certainly not do that because it's probably too complicated rather than just putting the brackets. But yeah, maybe if you want to do more complicated things like commutators or Lie brackets, you could code them in this way, or cats or whatever. You can even custom define some things on the fly. You could do some, if you wanted to do some delimiters like that, you could code them like delim, and then you say opening bracket is this, closing bracket is that, and then you apply it to whatever you like. Or maybe graded commutator, opening and closing, opening square bracket, closing braces, and in the middle you put some character that doesn't really sound like a delimiter, but you can do it. But the nice thing really comes here is that you can change the way they look by simple modifications. So if you were to write this here as a bracket, you could just add a S or C or A in brackets to say this is a square bracket or a curly or an angle bracket. And you can say, well, let's have them a bit bigger or even much more bigger, and or even as big as it needs to be, and thus you can easily create some compositions like that. You can even, and that might be useful for multi-line stuff, you can split brackets across lines. So you could say, okay, on the first line I open it, on the second line I close it, and if I want to change something, both of them change at the same time. Unfortunately, you cannot measure how big it has to be, but okay. It also helps you a bit in proper spacing. But on to the second package, if I have more time, yeah. So this is equation lines, and this is about convenient and adjustable multi-line equations, much like in the way you probably use AMS math. But it offers you one environment to rule them all. It's just called equations. There's a short form for equations. You can just use much like this construct that you probably use. You could use that for multi-line equations. I'm here to make your life easier, and that's what I'm doing. You can also put them within equations as a box and use the same short form. But maybe most importantly, you can also, and most of the time you won't need that, but you could modify that, the appearance of your equations. I want to highlight two sample applications again. How about placing numbers in equations, or how about changing the alignment? So yeah, you've probably used multi-line equations with numbers, but if you want to turn them on or off, you have to put stars somewhere, and here the feature is you could just put a star to turn them off in one place, or you could turn them on if they are somehow turned off by default with another simple character. You just add that, and you could, as usual, number all of the equations and then disable individual ones, but you could also put them as sub-equations with a simple just modifier like this. You could number just a single equation. You could do it with the first one, you could do it with the last one, or you could put it in the center. In normal LaTeX, that would require you some bigger constructs. And here in integrability, we like things like that usually occupied 2 pages before, and afterwards you can just do it in a line, and I'm just doing this on the level of LaTeX here. Okay, you can do other adjustments, and also if the number doesn't really fit where you put it, it will just automatically go elsewhere. So you don't bother with this kind of stuff. Another thing is alignment. Normally you often want to split equations. You have very long equations, you want to split that. You put this in an align box like this one here, but you have to say where the alignment mark is, and but the problem comes about when you have equations which are somehow occupying 2 lines. Now you have to either accept it like that, or you have to add a bit of space, or maybe even some more space here. But you could also just align it in the way with this new environment. You could just align it in the way that this plus comes right after the equation mark with kind of simple tweaks. You just say, okay, you want the equation mark to come before this character and not after it. You could also do something like gather, where there's no alignment at all, or something like multi-line, but the nice thing is it's all in one thing now. And there are further features like, I'm not going to say that, but you could have a look if you're interested, and hopefully you'll enjoy that a bit. And afterwards you can return back to integrability and go back to quantum mechanics and spend most of your day doing just that. So back to quantum algebra. So my next goal is to derive the Magnon scattering from the quantization of the algebra that I've described in the first part of the talk. And roughly, you could think of it in this way. So you have a quantum R matrix, which is composed from a rotation generator and a translation generator, typically divided by the difference of the spectral parameters. That's how it normally looks like. And even for this Poincare algebra, it really takes much like this form. But yeah, okay. Now for our purposes, we want a scattering picture, so we want to apply this to the scattering of two magnons. Magnons have momenta and masses and whatnot. So we just take a representation of this R matrix for particles, and then the R matrix you could view it as an S matrix. Now, if you just stare at what this R matrix does here, well, the first factor here is an L. It's a rotation. It will rotate the momentum of this particle, but it doesn't do this in a straight way, but it actually does it in such a way that it depends on the momentum of the second particle. So if you have two particles coming in, one momentum is rotated depending on the other particle's momentum, and vice versa. And then the next complication is that usually the quantum R matrix is an exponential of some differential operator. Now this is a shift operator. This does an infinitesimal shift. If you exponentiate that, that will be a finite shift. So you have two momenta coming in through the R matrix of this Poincare algebra, and it will somehow be the momenta will somehow be transformed from P1, P2 to P1 prime and P2 prime, or as the order is interchanged, it's actually P2 prime and P1 prime. Now, this is a bit difficult to actually compute. So we thought, okay, we can just look at the coproduct in this Yangian, which takes a fairly standard form, and derive some relations on these momenta. And actually, these give you 6 relations on 6 unknowns, so you can actually determine what is the outgoing momenta from the incoming momenta without actually touching the R matrix. And in this way, you find a certain transformation of the momenta that this R matrix should generate. I should note, though, that this is not a standard 3D scattering process because we do have particles which are still on a line. We still have the 1D line, the spectral parameters, but the particles have a certain spin, and this spin is a 3D Poincare representation. So that somehow governs how these are transformed. But it's not a real 3D scattering process in that sense. Okay, so now let's recall that we had, for this reduction, we have to reduce this 3D Poincare representation to one dimension, and that required us to do a certain twist of the classical R matrix. This was the classical twist. It's a combination of a P plus generator, momentum, and the L0, the Cartan generator of the rotation. So it's a rotation around the z-axis, or, well, actually the energy. But it's a particular kind of twist. It's a non-abelian twist, and it's actually a Jordanian twist that we heard in Sibylla's talk. And if you take the quantum version of that, it takes this form with an exponent of a certain log. Now you can apply this twist to the coproduct, and then you get the coproduct for generators. I've just taken some primitive generators. This might be L plus minus or P plus minus. If you just take that, you'll find that coproduct twists to this form. And that is something that was actually observed in the ADS-CFT Magnon scattering context, where, however, this combination was not labeled as 1 minus p squared, but rather as some generator, which I called u, which was called u, or e to the ip. So if you identify 1 minus psi p plus with e to the ip, where p is this Magnon momentum generator, then actually this form of the coproduct is what was actually found for the coproduct in the ADS-CFT matrix context. This twist parameter has to be 1 over the coupling, and yeah, then you do get for p plus exactly the form that I started with. But this picture so far, I've just replaced p plus by something else, by a different name for this generator. And something like p minus would be very different now. Actually, the Jordanian twist is very non-democratic. It's very different for plus positive charge generators and for negative charge generators. In fact, plus will be very simple. You can even do eigenvalues with that. But P0 would be more complicated. P minus would be even more complicated. But we have to reduce the algebra generators even more. We wanted to go from 3 momentum generators to 1 momentum generator, but we can do this by reducing p minus in much the same way as we changed p plus. We can actually relate 1 minus psi p minus to the inverse of this generator. That creates some relation among the generators, and we can also impose some relation between the P0 and P plus, but P plus at a higher level of the loop algebra. And that would implement the other relation, the last relation for the momentum generators, in which we learned in the classical picture, but this is how you lift it to the quantum algebra. And also, the Lorentz rotations can be reduced from 3 individual generators to just 1. And here again, the loop level somehow plays a role. Okay, I should probably come to a close, but I wanted to show you at least this picture here where you can somehow see how these momentum and the momentum reduction and momentum scattering through an R matrix work. So recall the magnons in ADS-CFT are labeled by some momentum, say P1 and P2. And in this giant Magnon kinematics picture, you could see them as some pieces of a pie, and they are somehow, if you just line up these pieces according to how they chain up along the chain, you get such a picture. Now, these 3-dimensional or the 2-dimensional px py momenta could be seen as the arrows going from one end of this segment to the next end, and if you chain up these segments in this way, you obtain a sequence of momenta. And what this Poincaré scattering process does for you is it basically just interchanges the order of these two segments of pi, right? So before scattering, you have these two momenta P1 and P2 prime, and after scattering, you have P2 and P1 prime. And the way they are related is actually just by using this non-abelian twist. So the purpose of this non-abelian twist is actually to shift this segment of a pi from its sort of rest position, like the first one, by just rotating it as much as needed to align it with the first particle. And also for the second one, for the resulting picture, you move this segment of a pi from the rest position by some amount to just make it match up with the first Magnon. And that somehow seems to be the role of this non-abelian twist, which is curious. And maybe also, what's interesting is that here you do have a proper mass shell relation. However, the mass shell relation is not centered at the center of the circle, but rather at the perimeter of the circle. So magnons at this position here have the lowest energy, whereas the energy raises until this maximum here at p equals pi, and then it sort of reduces back to its usual form. That is precisely the Magnon dispersion relation that you have. I don't have really time to mention the affine derivation. But yeah, you can lift this affine derivation to the quantum picture, but the problem here really is related to the to these extra poles, and it's very difficult to lift a classical expression to a quantum expression unless you can follow the usual recipes. Here we have additional singularities, so that makes it very difficult, and it leaves you. In this construction, leaves you with several ambiguities that you have to resolve somehow, because there will be one expression that works well. And for that, you can change even the classical picture. You can actually do a transformation on the U plane to remove this. Namely, you can do this Möbius transformation, which interchanges these two special points where U is plus minus 2 with psi equals 0 and infinity, and then the points 0 and infinity in the U plane get mapped to psi equals plus or minus 1. It's just a coordinate transformation, but it somehow makes all the algebraic relations in the classical algebra simpler. We hope that we can make some progress with that, and then come up also with a proper quantum version, in particular for the shift operator, which should be an additional symmetry for the R matrix. In principle, we can construct it, but it would be much nicer to get the full algebra relations for it. So I think I have to stop at this point with just this one conclusion slide. So I've discussed classical algebra for the worldsheet Magnon scattering, and we've constructed basically the full classical picture for it. We've related it to combinations of simple affine superalgebras, and this is nice because for simple affine superalgebras, all the construction techniques can be applied in a more or less straightforward fashion. Even in the quantum, for the quantum algebra, it's straightforward, but it's still very complicated combinatorially, and our quantum construction is thus ongoing. We still don't really have a full picture for this quantum affine derivation, but by investigating it further, we can maybe know or learn more about the non-difference form of the R matrix. We would like to know how the quantum R matrix can be contracted and reducted in much the same way as we did it for the classical picture, and I'd always be curious about other applications of this reduction procedure, where you take an algebra and somehow, or not just an algebra, but an algebra with a co-algebra that is a bi-algebra or a Hopf algebra. Take a Hopf algebra, you want to somehow make it smaller. You cannot really normally take a sub-algebra, because a sub-algebra will not really work together with a co-algebra structure. But this reduction scheme somehow takes that into account, and would be, of course, curious to see if we can not only apply this to a simple Poincare algebra, but maybe to more elaborate algebras. That would be curious to see. So thanks very much for your attention, and have a good afternoon.
Thank you. Thanks for the talk. Any further questions? I have one question regarding where you had the two R matrices, the D and the SL2 one. You said you had two spectral parameters in there.
Yeah.
And even after the contraction, you still had two free ones. So does that satisfy a Young-Baxter equation where you would say have a vector of spectral parameters, or?
What can I say? You basically have, one thing is that in addition to the derivation, you also have a second derivation which does translations in the second spectral parameter. The way this Poincare algebra works, and also this contraction procedure works, is basically that you have two identical objects, and then you sort of say they are identical up to a tiny bit. Now, you identify the two, that makes two, out of two algebras, it makes you one, and that is, so you just get the Lorentz rotations. But there is sort of a generator that measures the distance between the two, and that's the momentum generator. But this is a small one, it's tuned to be very small. So Or maybe sometimes it's the opposite. But anyway, there's always a large quantity and a small quantity. And the second spectral parameter, to a large extent, just behaves like it was this, an infinitesimal, just the first derivative part of something. So it's sort of always by construction a linear thing. It's simpler than all the rest. It's much like you take d by d u and just multiply it by v.
I see, okay, thanks.
But yeah, I don't know what the purpose of it is, and I would be curious to see. I haven't really mentioned that, yeah.
Any further questions? If not, then let's thank Niklas again. And enjoy the rest of your day.
Save them in a safe location. You can put them tomorrow when we